This is the first part of my video series investigating Riemann's hypothesis. We will start the introduction from freely accessible sources, mainly Wikipedia. In mathematics, the Riemann hypothesis is the conjecture that the Riemann zeta function has its zeros only at the negative even integers and complex numbers with real part half. Many consider it to be the most important unsolved problem in pure mathematics. It is of great interest in number theory because it implies results about the distribution of prime numbers. The Riemann zeta function is a function whose argument s may be any complex number other than 1, and whose values are also complex. It has zeros at the negative even integers, that is, zeta s equals 0 when s is one of -2, -4, -6, these are called its trivial zeros. The zeta function is also 0 for other values of s, which are called non-trivial zeros. The Riemann hypothesis is concerned with the locations of these non-trivial zeros, and states that the real part of every non-trivial zero of the Riemann zeta function is half. Thus, if the hypothesis is correct, all the non-trivial zeros lie on the critical line consisting of the complex numbers half plus it, where t is a real number and I is the imaginary unit. An equivalent statement to Riemann hypothesis, but for the trivial zero is: the imaginary part of every trivial zero of the Riemann zeta function is 0. The Riemann zeta function is defined for complex s with real part greater than 1 by the absolutely convergent infinite series. It equals the Euler product, where the infinite product extends over all prime numbers p. The Riemann hypothesis discusses zeros outside the region of convergence of this series and Euler product. To make sense of the hypothesis, it is necessary to analytically continue the function to obtain a form that is valid for all complex s. Because the zeta function is meromorphic, all choices of how to perform this analytic continuation will lead to the same result, by the identity theorem. A first step in this continuation observes that the series for the zeta function and the Dirichlet eta function satisfy the relation within the region of convergence for both series. However, the zeta function series on the right converges not just when the real part of s is greater than 1, but more generally whenever s has positive real part. Thus, the zeta function can be redefined as eta s divided by 1 minus 2 over 2 to the power of s, extending it from real s larger than 1, to a larger domain, real s larger than 0, except for the point where 1 minus 2 over 2 to the power of s, is 0. In the strip real s between 0 and 1, this extension of the zeta function satisfies the functional equation. One may then define zeta s for all remaining non-zero complex numbers s by applying this equation outside the strip and letting zeta s equal the right-hand side of the equation whenever s has non-positive real part, and s doesn't equal 0. If s is a negative even integer, then zeta s equals 0 because the factor sign pi s over 2 vanishes. These are the trivial zeros of the zeta function. If s is a positive even integer, this argument does not apply because the zeros of the sine function are cancelled by the poles of the gamma function as it takes negative integer arguments. The value zeta 0 equals minus half is not determined by the functional equation but is the limiting value of zeta s as s approaches 0. The functional equation also implies that the zeta function has no zeros with negative real part other than the trivial zeros, so all non-trivial zeros lie in the critical strip where s has real part between 0 and 1. Riemann zeta function along the critical line with real s equals half. Real values are shown on the horizontal axis and imaginary values are on the vertical axis. The function is plotted with t ranging between -30 and 30. The real part, red, and imaginary part, blue, of the Riemann zeta function along the critical line in the complex plane with real part equals half. The first non-trivial zeros occur where both curves touch the horizontal x-axis, for complex numbers with imaginary parts equaling plus or minus 14.135. plus or minus 21.022 and plus or minus 25.011. The animation shows the relationship between zeta function and prime counting function. It shows corrections to an estimate of the prime counting function using zeros of the zeta function. The magnitude of the correction term is determined by the imaginary part of the non-trivial zero being added in the correction. Several sources point to complexity of zeta function as the reason why proving Riemann's hypothesis is hard. It means that zeta function has some sort of irregularities or unpredictable behavior that is hard to describe in a short statement. Thus, solving the problem would involve simplification of patterns closely related to zeta function. In other words, its irregularities need to be filtered out. That's what we'll try to do in the next video.